Mm. children. Hello, everybody. I'm fixing the 4.4. Oh, no, that's not the one. That's not right either. So annoying. Hang on. Edit. Every time I try to edit, somebody comes in meeting room. So let's see. So I'm going to open it till 5 o'clock today. So if you emailed it to me, if you would please resubmit it through the submission thing, and I apologize. But it's not the most efficient way to do things, the way our Canvas is set up. Because I use Canvas at USF all the time and there's no issue. It copies whatever I tell it to copy. So I think it's just a SDHC thing. So you should be able to upload 4.4 homework.
There is there's no submit button for the 4.4 chain rule assignment.
I just fixed it like 2 seconds ago. Did you just try within the last few seconds?
Yeah.
You did?
I did. Yeah, and it says submitting on paper.
I must see. The due date change. All right, hang on. I can't deal. Okay, the on paper was my fault. I thought I hit online, so I am sorry. And the date is the 20th today, right? At 5 p.m. Is that what you see? Now there's a part 2 that I copied over. I better check that right now. So I copied over a part 2, which is due on Thursday at 11:40. So I did fix that. Well, let me make sure I have the submission there because who knows? Yeah, file upload, it's there. Okay. And oops. And then chain rule worksheet. And a file upload. Okay, so I fixed them, hopefully. But the deal is that Friday is my last day. So I'm not taking anything beyond Thursday, although the majority of you turn in your work when it's due. I have to say, I brag about you guys all the time. You turn in your work when it's due. Granted, it may not be the greatest, but at least you submit it. And most of you actually do very nice work. You write everything down, you keep it neat and concise and all that stuff. So, you're on your way. Now, I don't know if you saw my hot off the press announcement a little bit ago, but we just got notice from AP that you guys are all going to take your AP exam online next year, which is not cool because I think they gave the kids, I'll have to find out next block because that's my BC class and they had to take it online. It's a much more difficult test because you only have like 5 or 9 questions and you have like an hour and a half to do it all in and it covers everything. And so the kids said the paper and pencil test would have been way better because we'd have a better chance of passing. Now, a lot of kids passed, some didn't take it. So they didn't have to last year. They were exempted from taking it. But this year you must take it and you're going to have to do it from home online. And why they did that, I have no idea. I think it's a money-making thing. It probably saves them money to do it online or something like that versus printing out the paper. And they have these very sophisticated technology for plagiarizing, and it's very difficult to cheat. As I was telling the kids, the guy last year, we had to have a webinar, and he was salivating. He's like, let him cheat, because we're going to nail them when they try. And I was like, oh my God. So while I agree that kids should be nailed for cheating, they shouldn't be cheating. They were bragging about that thing. So the kids, the BC kids said it was much more difficult because they had less time and they had to cover everything in like an hour and a half. So I don't know how that's going to go, but I'm kind of glad that I'm not going to be part of AP. So again, I posted also a remind account for you guys. I made that this morning. I posted an announcement to sign up for it. That way we can keep in touch. So if you have questions on topics or anything that you want me to make a video on or whatever, then I can do that. All right. So let me give the test back to the children in class so they can have them. Because unlike the children online, you get yours right away. So this is block 3. Yeah, here we go. I'm almost done. Is Brian here? Where's Brian? So you'll see a lot of writing. A lot of writing. But you guys didn't do that bad. I mean, you could have done better, but you didn't do that bad. Alan. Stanhouse is not here. Matt. Matthew. And this one does not have a name, so I'm assuming it's yours. Is that yours?
Yes.
Okay. That's all right. So, yeah, it's kind of hacked up a bit, but just letting you know, you could have done, it could have been worse. And I'm not doing that. So like I told the last class, you guys are new to this stuff and it's going to take training and practice to get you up to par. So this is one of the reasons why I'm really, really adamant that I hope they get somebody with AP experience to teach you guys. Because if they don't, and we've got teachers here, half of our department, is brand new teachers. They're not even certified, okay? And I'm not saying that to bash anybody. I'm saying that because they don't have experience. So I'm worried because if they just let you do whatever they want, whatever you want to do or however you want to do it, that's going to cause you to lose lots and lots of points on the AP exam. So I'm not doing this to be mean to you or to because I want to see you get 20 out of 30 instead of, 29 out of 30. I'm doing the same thing an AP grader would do. And so it's really, really important that, that you understand that I'm hacking up your paper to help you, not to hurt you. And it's called tough love in a class of this level. And what that means is that I've got to be very, very strict and very, very firm in the way that you write things and the way that you display things mathematically, because that's how you're going to be graded in the end game. Okay, that's the end game. And your end game is to get a 3 or higher on the exam. So that's what I want to happen. I want you to be successful. And so that's the method to my madness. Okay, and you're not used to having to write like that. In pre-calculus algebra, probably most of you just walk through the class with your eyes closed, not much homework, piece of cake. But here, it's a different ball game. And again, you have to be very precise and very specific. And that's the way it is at all levels at college level. And this is a college level course. So anyway, enough about that. Let's talk about our agenda. So you did the product rule, you did the quotient rule, you did the chain rule, yes? Did we do some chain rule last week? We did, okay. Section 4.4. We're going to continue on with chain rule because I cannot stress the importance of you knowing how to use that rule, because your functions are going to be very complex. They're going to be composite for the most part, and you're going to have to know how to deal with it to take those derivatives. And so we didn't look at the natural logs though, did we last week? The composite natural logs, or did we? Did we look at any of those? Okay, so we're going to do more practice today, all right? So in Canvas, you're going to see a 4.4 part 2, and then you're going to see a chain rule worksheet for extra practice. And I'm not trying to kill you before Thursday. I really am not. But my hope was that we could get to related rates before I went away. That's not going to happen because you need to learn implicit differentiation. So after your quiz on Thursday, so you're going to have a quiz on 4.1, 4.2, 4.3, okay? Product rule, quotient rule, basic derivative rules. And if you're good with the basic derivative rules, then you don't need to study that. But if like the product rule you're a little bit, on, then you need to work on that, all right? You need to study for that. But chain rule, you will have a bonus question on to see if you can get some extra credit. And I wouldn't like overly study the chain rule, but you need to learn the chain rule kind of fast. It's on the curriculum, it's one class period to teach it, learn it, and done. So I want to give you some extra practice. And then after your quiz on Thursday, which please bring your laptop or a tablet or something because it's going to be on WebAssign so it can grade it for me very quickly and then I can just transfer that. Make sure you, we'll do implicit differentiation, all right? Which is a whole nother thing. But you need that to do good in related rates. You can't do related rates without implicit. And I will let the department head know where I ended with you guys. And then we can keep practicing, like I said, after the fact. I just have to kind of get my schedule together next week to see, when I'm going to be busy working and when I have time for you guys. So I will make the time. So fear not, just be on the lookout and I'll send you a remind message. So please make sure you sign up for remind because that's where I'm going to announce all of my live tutoring sessions and work sessions and whatnot. All right. Okay, so enough of that. So let me get out of here. Let me stop sharing here. Stop sharing. And let me check one thing here, of course. All right, let me go to my iPad. So were there any questions on the chain rule from the homework? Anybody? Online?
Over the last one,
The last one, which was what, 19 or
I think it was 21.
21? Okay. 4.4. Any others? Remember, the crystal ball is at home in all of the boxes with all of my junk from the school. So please tell me if you have questions, because again, I can't even go into the depth of the importance of knowing this rule inside and out. So number
21.
I'm sorry?
21.
21, yeah, that one was asked for. Any others besides 21? Anybody?
19.
19. Any others? Anybody? Going once, going twice? All right, so let's look at number 19 first, since it's lower on the totem pole. We have f of x is equal to the tangent root x, okay? I know this is composite because I know this function. There should be just an x in there, right? And there's something more than an x in there, which means it's a composite function. So I'm going to have to use chain rule. So, you can write this. Well, let me say this. The outer function here, which I'll call f, is the tangent of x. And that means the inner function is x to the 1/2, right? And I'm writing it in rational form so that way we can take the derivative easily. So the derivative of the outer function is the secant squared of x, and the derivative of that inner function is 1/2 x to the minus 1/2. Now, the chain rule says that if you have a composite function and you want the derivative of that composite, then that's equal to the derivative of the outer function recomposed with the stuff inside, which is called g of x, times the derivative of the inner function. So if I've got my f prime here, all I have to remember is once I take the derivative of the outer, put a parenthesis where the x is. So I would say f prime, well, let me write it here since it's already here. F prime g of x times g prime of x is equal to secant squared, what goes in my parenthesis? Square root of x, g, good, times the derivative of g, which is 1 over, I'm going to write it like this, 2 root x. Is that okay? Make sense? And that's it. So you might have seen the answer written as secant squared root x over 2 root x. And just remember, you cannot cancel those root x's, right? These are not cancelable. So you would leave it just like that. That was number 19.
I thought the derivative of root x would be 2x. Well, I guess no. I guess it'd be 1/2 x to the negative 1/2.
Right. Here it is right here. But if I simplify that, that's 1/2 x to the positive 1/2, which is 1/2 root x. You see
Which
that?
way is better to write it?
Well, if you're simplifying, definitely this way. Okay, so you'd want to simplify it like this. Because a lot of times what's going to happen is once you learn how to use this very proficiently, you're going to have to apply it to something. It might be an optimization problem where you have to find the, I don't know, height of the tallest mountain in the world or something like that. Or the biggest volume open top box, or a hiker that's stuck in the woods trying to get to her car in the least amount of time, or something like that, where you're going to actually have to plug the stuff in for X, let's say. And if it's like this, then it's harder to compute. That's all. All right. But also on the AP exams, although now that means, here's the other thing that means. On the regular exam, it was 2 parts multiple choice, calculator, non-calculator, and then 2 parts FRQ, free response, calculator, non-calculator. Now it's all going to be free response. They don't give partial credit either. So be prepared. So I was going to say that on multiple choice questions, you would see it written like this as an answer choice. They're going to simplify it. But now you're probably not going to have multiple choice on the exam. They swore up and down in the summer that they were going to have a regular exam this year. So I don't know what the deal, why they changed it, but they did. Anyway, 21, y equals x e to the 2x. So the first thing you have to recognize is that this is a product. And if it's a product or a quotient, you have to write out the product or the quotient rule first. So I have to say y prime equals x times e to the 2x plus e to the 2x prime times x prime. All right. And then what happens is you notice that within my product rule, I'm going to have to imply the chain rule. So you always write out the product or the quotient first, and then you chain as a result of whatever you're taking, what factor you're taking the derivative of. So if I take the derivative here, I'm going to have x times, now what's the derivative of this term? E to the 2x. Quick. Nice, 2e to the 2x. Okay. Everybody okay with that? Plus e to the 2x. Derivative of x is 1. So what you end up with is 2x e to the 2x plus e to the 2x. And he probably wrote the answer by factoring out an e to the 2x as 2x plus 1. You okay with that? So it's really, really important if you have a product or a quotient that you employ those rules first. And the grader will know because you're here, I'm writing out the product rule. And then the terms that contain a chain or a composite function, then you use the chain rule. Are we good? Or are there any more questions?
Miss Wilson?
You cut out for a second. For me, what did you say? Like you said you always do something, and then you cut out for me.
Say that again.
You said something about how you're always supposed to do something, but I didn't catch that part.
Oh, so when you have a product or a quotient, so this is a product, right? X times e to the 2x. You have to write out the product rule first. Or if it's a quotient, you would have to write out the quotient rule first. So this is the product rule. I'm telling the grader, I know this is a product. And then I have to recognize that since this derivative contains a composite, since this function contains a composite, then I have to use the chain rule to find its derivative. So the product or quotient rule comes first, then you chain the factors that need to be chained.
All right.
Somebody else was going to say something?
Yeah, so what's like if you didn't go to this very end part where it's like e to the 2x multiplied by 2x plus 1,
Mhm.
like what's the maximum you could have gone to still get that same amount of points?
The maximum what?
Like if you didn't simplify, would you still get the points?
It depends. They're going to be very specific and they're going to tell you to simplify. And if you don't, then you won't get any of the points. And if you do, uh, and if they don't say simplify, then you don't have to simplify and then you would get the points. So you could stop right here.
Okay, so they would tell you to simplify. It's not like
Yeah,
implied.
they would tell you they want it simplified. And the
Okay.
other thing is, so observations from the test. Some of you, so I'm just going to use this problem here as an example, but some of you just wrote an answer. Okay, that right away, you're not going to get anything for that. You will never get credit for an answer only on the AP exam. Now, if it's a power rule type of thing, like y equals 3x squared, and you say, okay, well, the derivative is 6x, that's a no-brainer. But product rule, quotient rule, chain rule, implicit differentiation, you must show the work. Not only that, but some of you were doing like, you were going like, x over here and e to the 2x over here, and then, you had some arrows. Some of you were writing product rule. Never, ever, ever write down what rule you're doing in words, ever. You will not get anything for that, okay? They know that you know the product rule if you use the proper mathematics. You only want to show it mathematically. Never, ever write this down. Very bad, all right? So, and you would write product rule, and then the product would be taken over here. And so, instead of seeing y prime, a lot of you weren't using the notation. If they give you f of x, equals 3x squared, right underneath that, you need to put f prime of x equals 6x. It needs to be concise, neat, organized. So you know how if you had me last year in pre-calc, in your notebooks, I had you draw a line down the middle and I made you work in columns. This is precisely the reason. Because by forcing you to do that, you keep that work in one centralized area. But if you've got your work all over the place here, or if it's not legible, the grader doesn't like turn the page and say, oh, there's what he meant for number one. No. It does not work like that. If the rest of your work's on page 2, it doesn't get counted. So in other words, if they're looking at number 2, and you've got stuff over here and stuff over here and stuff over here, and there's not the right notation, they're going to do this plus 0. It's as simple as that. They're not going to hunt around for your work or anything like that. It's either there or it's not where it's supposed to be. So if it helps you, do your work in columns, starting with 1 and work vertically, and that'll help you keep your work where it needs to be for the exam, right? Because those graders do not mess around. I promise you.
For the question that we just did,
Yeah.
where exactly did you use the chain rule? I know how you used the product rule, but where did you use the chain rule?
Where did I use it in this problem right here?
Yeah.
Oh, right here, this factor here, because this is e to the sum. So remember that if we have e to the x, we know that derivative, but when there's e to the something other than just x, anything, it could be x plus 1, it could be e to the 2x, it could be e to the sine of x, it could be anything. If there's anything in an exponent other than x, if there's anything in a trig function other than an x, if there's anything in parentheses other than an x, if there's anything under a radical other than an x, you need to use the chain rule. So right here is where I said, oh, this is not e to the x, this is e to the 2 times x. So that means it's a composite function. I had to plug 2x into here in order to get e to the 2x. Does that make sense?
Yeah, but where did you implement the chain rule to
Right
get
here.
the right answer?
Right here. So with e to
But
the x,
is that f prime of
Yeah.
g plus?
no. Okay, so the chain rule says if we have a composite and we take the derivative, we get derivative of the outside recomposed with the inside times derivative of the inside, right? f prime g of x times g prime of x. So this piece right here, this is 2 times the derivative of e to the 2x, if you want to think of it that way. Or actually, I'm sorry, I'm looking at the wrong one. It was this piece, e to the 2x, right? So what I know is that the outer function, and you don't have to write all of this, okay? You're not expected to. You're expected to be pretty proficient at it once you get used to it. But if it helps you, do it for now. But the outer function is e to the x, and the inner function is 2x, right? So the derivative of the outer function is just itself, and the derivative of the inner function is 2. So if we put this back together in this format, we have the derivative of the outer recomposed with the inner times derivative of the inner, which is 2e to the 2x. Now, e to the x is very special in many ways, but in one nice way is that when you have a composite function where you have a constant multiple multiplied to x, then what I want you to see is that you get the same function back times whatever that constant multiple is. So if I said e to the negative 1/2 x, the derivative of the outside is e, recomposed with the stuff inside, times the derivative of this thing inside would just be negative 1/2, right? So we'd write it as negative 1/2 e to the negative 1/2 x. So if there's a plus or minus or a sine or cosine in there, it wouldn't work. But if it's just 2 times x, 3 times x, 6 times x, negative half times x, it's going to be the same exact function times the coefficient of x. That okay?
Yeah, I understand that.
So are you understanding how I got this whole answer, this whole piece then, which I wrote right here? I took
That's not the same thing, is it?
Okay,
Well,
so
you just underline because that's 2x e to the 2x. That's
right, but at this point, this x is multiplied. So once I take the derivative,
oh,
I
okay.
multiply this x in. That's all I
Okay.
did. Mhm. Beautiful stuff.
Miss Wilson, you one of the examples you gave was e to the power of 1 plus x. Could you solve that, please?
That'd be e to the 1 times e to the x, right? Rule of exponents. Yes? E to the 1 is
Yeah.
e times e to the x. So this is a constant multiple. So it's e times derivative of e to the x is e to the x. So it's e times e to the x.
Oh.
Uh-huh.
Oh, okay.
Yeah. So see,
Well,
at this stage of the game, you're learning how to look at things differently. Go ahead.
for the last part of the original equation, e to the 2x,
Yeah.
when you're doing the chain rule, don't you need to do the chain rule for that as well?
Okay, so help me find, so you're talking about this over here, or you're talking about this over here?
The original function, basically. Yeah.
Okay, so this is the original function. Look, this is the original function, right? But this is x times e to the 2x. It's a product.
Yeah.
You agree with that?
Yes. Yes.
Okay, so what I must do is write out the product rule first, because first and foremost, this is a product of 2 factors. So I have to say that the derivative is equal to x times the derivative of this factor plus the second factor times the derivative of x. Here I'm employing the product rule. Now I need to take the derivative, right? I'm telling the grader here that this is the product rule. But now I need to actually take the derivative of each factor that I have this little tick mark on. So when I do that, I leave the x alone. The derivative of this is 2e to the 2x. So I've taken that derivative. Then I leave this factor alone, and the derivative of x is 1. And now I'm just multiplying in, what I can. So this is 2 times x times e to the 2x plus e to the 2x. And if I factor out an e to the 2x, I'm left with x plus 1.
You haven't done the chain rule yet. You just did the product rule.
No, I didn't. So look, this is the product rule, right?
Right.
This has been changed. This is from here to here is the chain rule. This is the only factor that needed to be changed, and it's right here.
Wait,
I think where you're getting confused is, so you help me out. You'll let me know if I'm wrong. So what I'm thinking is, so let me find something simple, like how about x sine of x? Okay, we'll say y equals x sine of x. So product rule, we write down y prime is equal to x times the sine of x, right? Plus the sine of x prime times x prime. You're okay with that, right?
yes.
Okay, now if we actually take the derivative, we have x cosine of x plus the sine of x. Do you agree?
Yes.
And I'm done, right?
No.
Okay, in this case here, I can't just do that. Why? Because I have a composite function right here, and I have to use the chain rule when I take the derivative of that piece. So I'm talking about right here. I have to use the chain rule when I take the derivative of this piece. This is the chain rule done. All right, I've used the chain rule. I took the derivative of the outer, recomposed it with the stuff inside, and multiplied that by the derivative of the stuff inside. So this has been chained right here. So this,
Okay, then don't you need to change the other e to the 2x?
no. The product rule says, so the product rule says that, you know, if you have two functions, f of x times g of x, then you leave the first factor alone and you multiply that by the derivative of the second factor. And you add to that the second factor times the derivative of the first. So in this term right here, I'm taking the derivative of g, okay? Whatever it may be. It might be a chain rule, it might be a quotient, it may be something simple. And in this one here, so here I'm leaving f alone and I'm taking the derivative of g. And this one I'm leaving g alone and I'm taking the derivative of f.
Oh, okay.
All right?
Yeah.
Make sense now?
Yeah.
You were making me nervous there for a minute.
Well, it was just
I know it's more more complex when you have a combination of things that you got to deal with. But what I'm trying to get with this is that more often than not, you're going to be dealing with these complex derivatives. Because while it's nice to have something like this every now and then, you know, what's the derivative that you can do in your head? The majority of the time, they're going to be products, quotients, chains, and a combination. So that's what I'm trying to get you to look for. All right. Have we done this problem here? Did we do this one yet?
No,
Look
I don't
familiar?
believe so.
Okay, find f prime of x for me. Find the derivative. Oh my goodness.
think I have it, but I don't know if it's simplified.
Okay, tell me.
X, the square root of x
Mhm.
times sine 3x times cosine 3x times 3.
Like this? Did I write that down right?
Yeah.
Okay. Well, we'll put a question mark because we don't know yet. I need that Jeopardy music so I can play it while you're doing the work. I'll doodle till I get another answer choice in. I can't draw. Oh yeah.
I got one. I'm also not sure if it's correct.
Give me 1 second. Okay, go ahead.
Okay. Sine of 3x plus
Ooh, ooh,
6.
Wait. My pencil was on. Okay, sine of 3x.
Plus 6 root x
Mm-hmm.
multiplied by cosine 3x
Mm-hmm.
all over square root of x.
Like this?
All over the square root of x.
Oh.
Yeah.
Okay. Anybody else come out with something different yet? Yeah.
The sine of 3x over square root of 2x plus 3 times square root of 2x times cosine of 3x.
Like that?
Yeah.
Okay. So this is not good, right? Got different answers. It may be good for, if one of these is right, it might be good for that person, but for the rest of us, it's not so good. So let's go over it. All right. The first thing I ask myself when I, the experienced teacher of mathematics, looks at anything, I don't care how elementary it is to me, I scan it from left to right and I say to myself, self, what am I looking at? I'm looking at a product, right? And if I need a derivative, then I need to employ first the product rule. So I do have a product here. This is one factor and this is the other one. So I'm going to write down the product rule. It's root 2x times the sine of 3x prime plus the sine of 3x times the square root of 2x prime, right? So there's my product rule. And then unfortunately, I look now in this first term, and specifically, I'm looking at the thing I need to take the derivative of, the factor, and I'm like, darn, it's a chain rule. I got to use the chain rule, right? So what I do for the greater is I say, well, this is equal to root 2x. Now, the derivative of this outer function is the cosine of x, but I'm going to recompose the inner function times the derivative of the inner function. Is that okay with everybody? So you get 3 cosine 3x. Is that all right or not?
Yeah.
It's good. It's good.
Okay, I was just about to say the silence is deafening here. And by the way, I'm going to write this factor over here as 2x to the 1/2 prime because, I can't take a derivative while it's in a square root. So I'm just rewriting it as an exponential power. So that way I can take a quick derivative. Now this too
Wait,
is
what
a
are you
change.
taking derivative?
I'm sorry.
Why'd you write that?
Okay, so this factor here, so it was
Just which one?
this root 2x. I'm just rewriting
Okay, that makes sense.
2x to the 1/2 power so I can take the quick derivative.
Yeah, okay.
All right, so we've got sine of 3x here. So this one doesn't change, but this one is the one I have to take the derivative of. And again, it's a chain rule, right? So I'm going to do that down here for a second. So the outer function is x to the 1/2 and the inner function is 2x. So the derivative of this outer function is 1/2 recomposed with the stuff inside. Don't forget to subtract 1 off of the power, right? So I'm using the power rule essentially. I'm treating this stuff inside as one big x. So my outer function is x to the 1/2. So if it's x to the 1/2, I'm using power rule. I bring down the 1/2 and do x to the 1/2 minus 1. But then remember with the chain rule, because this is a composite, I have to replace the x with the stuff inside, the 2x. And then I have to multiply that result by the derivative of the stuff inside, and that derivative is 2. Is that okay? So what I have over here for this term here is, and by the way, this 2 and that 2 are going to cancel. So what I have is 2x to the negative 1/2 here. Are we okay so far?
Quick question.
Yeah.
Is 2x squared a composite function?
Is 2x the quantity squared a composite? Is that what you're asking?
No, I was just asking 2x squared. Is that a composite?
Okay, but it depends on what when you say 2x squared. So are you talking about 2x squared or are you talking about 2x the quantity squared?
Well, I guess that's really my question is, so there's a difference between those two that would make one a composite and one not.
Right. This is 2x squared. In this form, it's composite, but this really, if I work this out, is 4x squared, right? 2 squared times 4 squared, or times x squared, right? So they're not the same function. Now, this is simple enough that I could square every little factor in there and come out with this. But it's composite in its form because I have an inner function, which is 2x. This is the inner function, and I have an outer function, which is x squared. You see that? This is the outer, this is the inner. The derivative of the outer function is 2x. If I recompose it, it's 2x squared times the derivative, oops. Hang on. The derivative of this outer function is 2x. If I recompose it with the inner function, it's 2 times 2x times the derivative of the inner is 2. That doesn't make sense. Hang on. 2x quantity squared. So it's 2 times 2x times 2. Did I make a mistake over here? Huh? 1/2 times 2x to the negative 1/2 times 2. I think I made a mistake. So this is 8x, right? No, that can't be right. This is not a good example. I'll tell you why in a minute. So the idea is this. I never want you to forget this, okay? From this day forward. If I have the square root of x, the sine of x, e to the x, x to the 1/2, those are not composites. The reason why is because under the radical, in the trig function, in the exponent, or in this parenthesis, there's only x to the power or x in the power or x in the function or x under the radical. There's only an x there. However, if I have anything other than x, no matter what it is, it could be root 2x, it could be the sine of 6x, it could be e to the tangent of x, it could be 4x to the 1/2. Anything other than x, then you're looking at a composite. Parentheses, powers, trig functions, or radicals contain composites if it's anything other than x. Does that make sense? Hello?
Yes.
Yes.
Okay, let's do another one, can we? Oh, wait, we didn't finish this one. Let's finish this one. So is this correct here? Did I do this right? So this is 1/2 x to 1/2 2x to the negative 1/2 times 2, the 1/2 and the 2 cancel. So we have 3 different answers up here. So I'm going to try and clean this up a little bit. Down here, I'm going to bring the 3 out front. So I have 3 root 2x cos 3x. Now this would be plus sine of 3x. This here I would write as 1 over 2x to the 1/2, right, to make that exponent positive. And then I realize that this is a square root, so I'm going to put it like this. Now, if we wanted to simplify, we would write this over a common denominator. So that'd be 3 times 2x cos 3x plus sine of 3x all over root 2x. Or this, you could write that as 6x cos 3x. So I have a 6 root x cos 3x plus sine 3x over root x. So something was lost in this one. I have a sine of 3x over root 2x plus 3 times 2 root x cos x. So this one is a winner here. And this one, we're missing some stuff. So whoever came up with this last one here, and that doesn't include this thing right there, I don't think, 1. You get 100 A's, not $100, 100 A's. Let's do some more. Let's do some more practice. Ay, ay, ay. Can you find y prime for me? And I need a piece of paper so I can do that other one. Yeah. Mm-hmm.
I think I have an answer.
Go ahead.
So 2 times the quantity x plus 1 over x
Mm-hmm.
multiplied by the quantity x plus negative x squared.
X plus x squared.
No, the quantity x, 1 plus negative x squared.
You mean x to the minus 2 or negative x squared? Because you said 1 plus negative x squared, so that's why I'm confused.
Negative x to the negative second power.
So
There's a
you
negative
have,
sign for the x too.
so
yeah.
here, like that?
Yeah. Yeah.
Okay. And who was that answered? That was Aaron? Is that right?
Yep.
Aaron got it right.
For this one, how do we distinguish what g of x is?
Okay, so G I always call the, so Aaron, I'm gonna remove your gorgeous work here. Or your gorgeous answer anyway. But, so we have an inner function and an outer function in every composite, right? What would you tell me the outer function is? I'm gonna call that F. What's the outer function?
X squared.
Good. So that means that the inner function has to be anything that's inside, inside the radical, the exponent, the trig function, or the parentheses. So what is the inner function? It's x plus 1 over x, right? And
Yes.
I would even write that as x plus x to the minus 1. Why? Because I know I have to take a derivative of that eventually. Is that okay?
Yep.
Yeah.
For the answer, the right answer, would we have to expand that, or can we just?
No, you usually never expand. Mhm. Did you get the same answer that Aaron got? Good.
Miss Wilson,
Mhm.
could you have written 1 minus 1 over x squared instead of 1 minus x to the power of 1/2?
Yeah, and in fact, I would. And I'll tell you why in a sec.
Okay, and for the second one, could you have written 2x plus 2 over x? Or no?
So here. So the derivative here is the derivative of the outer function recomposed with the inner, subtract 1 from the power, so that's just to the first power, times the derivative of the inside, which is 1 minus x to the minus 2. Is that what you got?
Yeah, I just didn't simplify the first one. I said 2x plus 2 over x.
That's fine.
Oh, okay.
No.
And then for the second one, I think it was 1 minus 1 over x squared.
Yeah, so remember that all of this is 2 times this thing, right? So if you just FOILed these two binomials out, and I would definitely write this like so. If you FOIL these two out, you're gonna have 2 times the quantity x minus, now x divided by x squared is 1 over x, right? So those two equate to 1 over x negative. This is a positive 1 over x. And then over here, you can have a negative 1 over x cubed, right? Is that okay?
Yeah.
Are you sure? Let me do it again. So if I just FOIL x plus 1 over x times 1 minus 1 over x squared, x times 1 is x, right? X times negative 1 over x squared is negative x over x squared. I'm just going to leave it like that for a second. Then 1 over x times 1 is a positive 1 over x. And 1 over x times negative 1 over x squared is a negative 1 over x cubed. This one right here reduces to 1 over x, right? And x cancels 1 for 1. So I have 1 over x plus 1 over x. Well, those two terms are going to cancel completely. So I end up with x minus 1 over x cubed. Now, if I multiply that by the 2 that was sitting out there, which I would have to, I would have 2x minus 2 over x cubed. That would be the most compact, simplified form of this. But if you're writing it out at this point here, this is the correct derivative right here. It's just not simplified.
And if you're simplifying, you'd have to keep the 2 going throughout the entire process, right?
Mm-hmm. Right, because again, this is 2 times this times this. This is all a product here. So once I find this product, then I can multiply in by the 2, or I could have multiplied the 2 in here and then multiplied it to that. You know, there's a lot of different ways a lot of different combinations I could use, but that's what it is.
No, I'm saying like how when you're multiplying, like when you FOILed, you'd have to have the 2 next to that, right? And then you have to
Yeah,
keep 2,
no,
right?
you would. I was being sloppy. I was being sloppy, so yeah. I just wanted you guys to focus on the 2 binomials, that's all. That's why I left it out. So in the real world, yes, that 2 would be brought down every step of the way, which is what you guys have to do. But if I'm trying to demonstrate or have you focus on something in specific, oftentimes I'll leave it out temporarily and then bring it back in.
Wait, so Ms. Wilson, in order to get this point, we would have to simplify, right?
Right.
Okay.
See, here's the big problem is that, you know, and probably most of you got A's in algebra, okay? I would like to know how this happens because when kids come to calculus, they can't, this is just basic algebra. Do you agree? This is not anything hard, but a lot of students have trouble with this. So I've got some students who are very good at it. Their algebra skills are top notch. And they will not have a problem in calculus because their algebra skills are strong. You have to have strong algebra skills to do well in calculus because it's not the calculus that will get you, it's the algebra that's going to get you every time. So in other words, on the AP exam, if they say find this derivative and simplify, a lot of you can get to here no problem. It's in here where you're going to screw it up somehow because you forgot a rule or you did some silly bad math thing, and they're going to nail you for it. All right. So the thing is that you've got to practice those algebra skills, and by us forcing you to simplify, you're constantly working on those algebra skills and they get better and better and better. And by the time the test rolls around, you know, you're going to get it. And by the way, my pass rates are not only stellar in this district, but my kids used to get straight 5s. It wasn't a couple of 3s and a 4 and a few 5s. It was straight 5s down the board. I'm not kidding. So the same can happen here, but we have to be really, really, really good at our algebra skills. And that's what's getting you guys. And it's not abnormal, by the way, in every school district across the nation in the United States of America with a K, our students think that they're really good at algebra until they take calculus. And that's when they realize that, maybe my skills aren't quite as good as I thought they were. All right. Or kids will say, well, I got A's, you know, A. So now all of a sudden I'm failing. You're a bad teacher. No. You're not as good as you think you are. All right. And it really does boil down to that. Even the colleges have issues with it. So it's not abnormal and it can be corrected. You just have to be willing to try to correct it by doing this mess here. Because there's a lot of this mess in calculus. So calculus, I always say, calculus, by the way, is a very low level math. I know it's high level for you guys, but in the world of math, it's very low level math. And I always call calculus the quicker picker-upper because you're really cleaning up a lot of messes. The derivatives are a piece of cake. Once you get the hang of them, you can do them. But to apply them and to clean up the algebra, that's the hard part. So just keep that in mind. You'll get better at it. You just have to practice. So I always want you to try to simplify because that's going to help you get better with your algebra. All right, here's another one. Y equals x squared minus 1 over x quantity cubed. Do it. What is y prime? Y prime is 100% dead on accuracy. And I want it simplified. Wow. simplify. Anybody? Yeah.
I got something.
Yes.
3 times the quantity x squared minus 1 over x
Mhm.
squared.
Good.
Multiplied by the quantity 2x plus x to the negative second power.
Okay.
I got the
But
same.
what's it simplified?
What is it simplified? Well, hold on and I'll show you. Oops. Hang on, I just have to plug in my iPad because my battery level is low. Oh, wrong side. Sorry, this is going to flip upside down for a second. My power cord is short. Here we go. Okay. So, oh yeah.
We gotta have it.
Okay, what's your simplified version?
6x to the fifth minus 9x squared plus 3 over x to the fourth.
Just the 3 over x to the fourth or the whole thing?
Just 3.
Like this?
Yep.
Carson, is that what you got?
No.
What'd you get?
X and then parentheses 5x cubed minus 2.
Mm-hmm.
No, minus 2 is down below.
Oh,
It's not x.
so like this. Uh-huh. This is the answer? Yeah, I don't know. So let's see. Let's see if any of these are correct. The outer function is x cubed, so the derivative of the outer function is 3x squared, but instead of putting an x in there, I'm going to refill it with the stuff inside. Everybody's cool with that, right? Everybody gets that? This is your f prime g of x right here, this thing. Times, now we're going to deal with the derivative of the inside of this thing, and if you want to, rewrite it like this for the derivative. So the derivative of that is 2x. A -1 times a -1 makes that a positive x to the minus 2. All right, and if I clean that up, we're going to have 3 times x squared minus 1 over x quantity squared times 2x plus 1 over x squared. Is that okay? Yes, no.
Or is it 1 over x squared?
Well, x to the minus 2. Anything.
Okay, minus 2.
You got it? Okay.
But
So-
wouldn't it just be easier to keep it as -2?
No, not if you're going to simplify it. I mean, I don't know. Maybe it is to you. I don't think it is, but that's my opinion. You could not do that. But the thing is that I want common denominators inside the parentheses. So I'm going to find that first. I'm going to have x cubed minus 1 over x quantity squared times 2x cubed plus 1 over x squared. And now I'm going to go ahead and square this second term. So I have 3 times. If I square this, what I'm going to have, if you want to square it at this point, it's okay. You're going to have x to the 4th minus 2x squared over x plus 1 over x squared. I'm going to leave it like the line above because I think this, if I do this one here, it'll confuse you. So I'm going to leave it like this. So I'm just foiling this, right? X squared minus 1 over x, that was an x there, times x squared minus 1 over x is x to the 4th times negative x squared over x minus x squared over x gives me negative 2x squared over x. So, and then negative 1 over x times negative 1 over x gives me positive 1 over x squared. If I clean that up, I'm going to have 3 times x to the 4th minus 2x plus 1 over x squared. And now I've got to distribute that to 2x plus 1 over x squared. And if you want to at this point, throw the 3 in there. So 3x to the 4th minus 6x plus 3 over x squared times 2x plus 1 over x squared. Now, if I FOIL this again, I'm going to have 6x to the 5th. Okay, so I'm not FOILing, I'm distributing. Plus 3x to the 4th over x squared. Okay, minus 12x squared minus 6 over x squared plus 3 over x squared times 1 over x squared is a positive 3 over x to the 4th. And then 3 over, oh, I forgot the 2. 3 over x squared times 2x is going to give me plus 6x over x squared. Well, look, these two are going to cancel, so that's nice. Also, 6x to the 5th plus 3x squared, right? I can cancel 2 for 2 here, minus 12x squared plus 3 over x to the 4th. I can combine those like terms, so I get 6x to the 5th minus 9x squared plus 3 over x to the 4th. And there it is, right here. Good job. So there's a lot of work involved to simplify something like that. I get it. I don't like doing it either. Well, I kind of find it relaxing, but I understand that it's a lot of work. My thing right now is if you can just use the chain rule properly, in other words, don't simplify, but employ the chain rule properly without simplifying. If you can get right here, I'll be happy with that because you can work on simplifying later. So for these homeworks that I posted, I want you to use your chain rule, your power rule, whatever you have to use, but don't simplify them. All right? Okay, let's see what else we have here. This is very important. I don't know if we did any of these, but what about the fact that, I don't know if I told you this, but the derivative of ln x is 1 over x. That's an important rule. The derivative of the natural log is 1 over x. So if you're given something like y equals ln 3x, right away that's not an x there, so you know it's a composite, right? What do you suppose the derivative is? What's the derivative of the outer function?
1 over 3x?
Okay, the derivative of the outer function, ln x is the outer function, so the derivative is 1 over x, but instead of x, we've got to recompose it with the stuff inside the parentheses, right? Times, what's the derivative of the inner function? 3.
3.
So you get 1 over x. Thank you. What about y is equal to ln 2x? What's the derivative of the outer function?
1 over
1
x.
over 2x.
But we're going to replace it with 2x, right? Times derivative of the inside. What happens to the 2's? You get 1
1
over
over
x.
x.
This is kind of like e to the x, isn't it? When you had like e to the 2x, you knew the derivative was 2e to the 2x. Well, with the natural log, again, as long as it's just, you know, a number multiplied to x, not a plus, minus, or anything like that, then the derivative is really easy. What if you're given something along the lines of this? Oh, did I go over the rules of logarithms from algebra with you guys yet? No? Yes.
I don't
don't-
think so.
Think so?
Okay, they're going to come in really handy in this section. So what I want you to remember is that the sum of two logarithms can be written as one logarithm of the product. This is the compact form, this is the expanded form. The difference of two logarithms can be written as the quotient of one logarithm. And if you have a constant multiplied to a logarithm, then I believe it's called the exponent rule, where you can write this as the natural log of x to the n. These are 3 very important rules that you learned in algebra, and they come in very, very handy in calculus. So it's really important to know these. Why, you may ask? Well, let me show you. F of x equals ln x quantity squared. Well, I say chain rule, right? Derivative of the outer function is 2x recomposed with the inner function times derivative of the inner function. So I guess I get 2 ln x over x. So I did that very quickly. Okay, I don't know what that noise is, but it's scary. But rather than that, if I know the exponent rule, I've got a logarithm in this form right here. I can bring that 2 down. I can rewrite this as 2 ln x. This becomes a constant multiple. So what's the derivative of ln x?
1 over x.
1 over x. All right. So the thing is here, something didn't work out again. Why is this happening to me today?
Well, wouldn't it just be 2?
No. Okay. All right. So let's look at this again here. Let's look at chain. Okay. The outer function, I'm going to call f is x squared. Do you agree with that?
Yes.
Hello? All right. The inner function is ln x. So the derivative of the outer function is 2x. The derivative of the inner function is 1 over x. Now, if I take f prime and recompose it with g, I get 2 times ln x times the derivative of the inner function. or 2 ln x over x? Yes?
Yes.
Okay. Let's just focus on chain. I know. Here's another one. Y equals natural log of sine of x. Help me out. What's the derivative of the outer function? 1 over x, but what am I going to replace the x with? The stuff inside. Good. The inner function, sine of x, times, now what's the derivative of the inner function? The sine of x. Well, that's the cos x over the sine of x, isn't it? What's a trig identity that you're familiar with for the cosine over the sine? The cotangent. Questions on that one?
Where did you get the 1 over sine x from?
It's the derivative of the outer function. So if
Oh, right, because it's 1 over x. And then
see
you
it?
multiply.
Okay. All right. I just want to make sure you see it. Mhm.
Going back to that one where it was ln x squared.
This one? Mm-hmm.
Would you be able to use the multiplication?
Right. So that's what I was trying to say. I could, so this right here is in this form here, right? So what I could do is I could rewrite it as 2 ln x, right? And then take the derivative of that. So let me move this. So if I do that, if f of x is equal to 2 times ln x, this is not making sense to me because that would be 2 over x, and we're losing an ln x, and I don't know why. Because it's no longer composite. I think it's a coinkydink.
Okay, so ln x squared would be multiplied ln x by ln. So that would be 2 ln.
Oh, yeah, thank you for, see, even I do it. Yeah, this is not ln x squared, this is ln quantity x. I'm sorry, yeah, good. Oh, see, bad. So that was a bad algebra skill I just employed there. Right, so this is ln x times ln x.
So if the square was on one side, then can you do that?
Yeah, if it were ln x squared, then you could rewrite it as 2 ln x. That would be 2 over x, the derivative. Okay, so good eye. But this is not. This is ln x, the quantity squared, so I wasn't paying attention, which is ln x times ln x. So what you have is a product rule, right? You have ln x times the derivative of ln x plus ln x times the derivative of ln x, which is ln x times 1 over x plus ln x times 1 over x, which is 2 ln x over x. You treat this 1 over x as a, the whole thing as a variable. Here's another one. Why? So this is more typical of the problems you deal with. 2x plus 3. Did we do this one yet?
No.
Okay. So the question is, can you find y prime? And while you're doing that, Cursor is here. Eric's here. Sana's here. Yoshi's here. Rachel's here. Adeline's here. Karsten's here. Joshua's here. Chatana's here. James is not. Shrew's here. Brian's here. Vivian's here. Is Ethan in the room? Ethan, are you here? I don't see Ethan.
So I think where I'm getting tripped up is whenever you use the product and quotient roots in tandem with the chain rules.
That's normal. So looking at the original function, what do you have? What do you have there?
We have ln minus, oh, ln 2x plus 3 minus ln x squared plus 4.
Okay, you could rewrite it like that, sure. But just looking at the original, at this thing right here, do you have a product? Yes or no? Is that a
No.
product rule?
No.
No. Is it a quotient rule?
No.
No.
What?
No. There's a quotient in there, but this whole thing is not a quotient, and this whole thing is not a product. It's a chain rule. It's a composite. That's why I threw it in here. So what you have is this outer function, all right, which is ln x. And you have this inner function, which is the quotient. So the derivative of the outer function is easy. It's 1 over x, right? But the derivative of the inner function, you need to use the quotient rule. You see the difference? So earlier when we were doing some practice, we had something like, I don't know, I don't remember what I gave you, but so something along the lines of say x e to the 2x. And we looked at the original and we said, hey, this is x times e to the 2x. I need to use the product rule. And then if any of the factors contain a composite, then I have to employ the chain rule. This is not the case this time. Now what we have is we have a composite, all right? And one of the factors happens to be a quotient. So we're going to have to employ the quotient rule. So the derivative outside is a piece of cake. The derivative inside is where I've got to use the quotient rule. Does that clarify it at all?
You know,
But the whole thing is not a quotient. So you would not use the quotient rule to solve it. This is where we have to train your eyes, my darlings. You have to train your eyes.
The quotient rule is fig plus gif over g of x squared.
Right. I'm kind of working it out because the bell's going to ring in about, I don't know, 10 minutes. So
an answer as well, but,
Mhm.
very long.
What did you get?
I got negative, 2x to the fourth, minus 6x, minus 24x plus 32. That's all over the 2x to the fifth, plus 3x to the fourth, plus 16x to the third, plus 24x squared, plus 48.
So you expanded this out here?
Yeah.
Never do that. So here's the thing. I did this problem earlier for the last class, so it's the only reason I knew, but generally speaking, if we're dealing with a quotient rule, if this looks factorable, we might try and factor this down so maybe it contains this factor here that we could cancel with. But I had already factored that down and it didn't, so that's why I didn't try this time. So yeah, we never generally ever expand the bottom out. It wouldn't be wrong, but it's more work.
Can you go back to your first step?
Up here?
Yeah, your first step in blue. Why is it 2x squared plus 4?
Okay. 2x squared plus, oh, right here? Right here? Because this is how I do the chain or the quotient rule. It's the derivative of the top always. You always have to take derivative first of the numerator. So derivative of the top is just 2, right? Times the bottom minus the top times derivative of the bottom over bottom squared. You with me on that?
Yeah, that makes sense. Okay, thanks.
Mhm. Anyway, we pretty much just practiced a bunch of chain. So let me just remind you that on, oh, don't forget to sign up for Remind. That's number 1. Number 2, on Canvas, there is, I'm going to share this screen. Let's see if I can do it. Share. Okay, on Canvas under assignments, the first chain rule homework is here. There's like 3 questions in this one. Let me just make sure that, yeah, 3 questions, 24, 32, and 33. That's not our bell. And then what I attached was a chain rule worksheet. And it's got some simple chain rule problems and some more difficult chain rule, some combination problems. So that way you can get practice in. I didn't attach a key because it's actually a solution key. Everyone has the solution. So it'd be just like copying your homework if you felt like it. But I want you to try it without the key to see how you do. And then we'll go over any questions that you have on Thursday after your test. All right.
So what should we study for our test on Thursday?
So I don't think any of you need to study for section 4.1, right? Basic derivative rules. They're included from now until the end of time. So that's going to be on there, of course. The exponential rules, the exponential function, so b to the x and e to the x, I think you're all probably okay with those. But the new thing on this test is going to be that it's going to include the product and the quotient rule. So really you just need to study for those 2 rules. And it's going to be multiple choice, but you are going to upload your scratch work to me. Okay? You're going to take it on WebAssign, so make sure you bring a tablet or a computer or your phone because you're going to have to access WebAssign that way. And if you have a laptop you can bring, that's even better because I can't imagine doing that thing on my phone. And I think on the phone, I think that sometimes the notations and stuff don't come up right on the phone. So please bring your laptop. I have 1 laptop in here that can be used. But that's the only thing, that's the only one I have. I have to use my computer to monitor you because you will have to have cameras on. So that's it. 4-4-3, no chain rule, except for maybe a bonus in chain rule, an extra credit, but that's it.
And so this is way the same as the other quiz.
Always. That's why I have the pass rates I have.
For AP, or for your like, for your class grades or your AP?
No. If a kid can perform on tests, because tests is really the assessment, right? If a kid can perform well at an 80% weight, then they're guaranteed to pass the AP exam.
Makes sense.
And yeah, in IB too, when I taught in IB, I did the same thing. So everything in IB has to be, because those kids can't get less than an 80% or they get kicked out.
Oh, yeah. My sister's might be impressed. And I tell her stuff, she's gonna be like, yeah, I'm really glad I didn't go through that.
IB is a lot of work for the kids.
It is.
It's almost criminal. They have a lot of
I
work.
would hate that, because it seems like a lot of menial stuff and just, I mean, I get
In
it.
some
comparison.
classes, but like in a calc class, for the SL seniors, I taught SL seniors in higher level, HL seniors and juniors. We flew through that stuff. And the SL seniors are pretty good in math, but they're not like great. HL kids, those are creme de la creme. Those kids were incredibly bright. But the SLs were more of a normal kid, just trying to get through. The HL, if you're in HL math, you are especially gifted in math, because otherwise you don't get in. So those kids, I would fly. But the SLs, I would have to slow down, but still in comparison to an AP class, they flew through it. And they would just be like, oh my God, Miss Wilson, I'm gonna die. I'm like, I know, I'm sorry, but you're having a test next week, so guess what? Deal with it. And so they would have to. But I did feel bad, but I had to do that because of the IB exam.
Do you think IB is worth it?
I don't. That's why I left. So I had a very nice job, and I was in IB for 9 years at Hillsborough. Great people to work with. I think the program's good, but I think that kids cannot be kids anymore. They have to do all kind of community service. They have to meet all of these requirements, and all they get is a blue piece of paper. They get their diploma, whether they go through IB or not, because they're smart kids. But at the end, they get a blue piece of paper that says they get an IB diploma. And I'm sorry, but those kids, unless they were HL, the HL kids had a life a little bit more, but the SL kids, no.
Yeah, my sister told me there for cheerleading, because Crest has one of the best teams in the country. That's the only reason why she goes there. But
She goes to Hillsborough?
Crest.
Okay,
Crest.
Strawberry Crest, yeah.
But it just seems so bad, you know, where she's only in sophomore.
Yeah.
She's.
So the junior year is the worst because they have they have to start their IAs and they have extended essays in the junior year. And then the senior year, they have the internal assessment, which is a nightmare in and of itself. So yeah, that's what I disagree with. It's just too much, I think, but.
All right, thank you.
See ya. Well, you guys can go. I'm sorry.